Today, we're dissecting CUDA, not the glossy marketing about accelerated computing, but the brutal reality where graphics cards became supercomputers, where parallel programming broke every assumption about software development, and where one company accidentally created the most successful platform lock-in in computing history. Three experts who have battled thread divergence at 3 a.m., debugged memory coalescing failures that destroyed performance, and learned why just port it to GPU became the most expensive lie in high-performance computing. I'm Sam, and someone just asked me why our GPU acceleration project is running slower than the CPU version.
I was part of the original CUDA team at NVIDIA. We thought we were building a nice programming interface for graphics researchers. We had no idea we were creating the foundation for the AI revolution and accidentally locking entire industries into our ecosystem. CUDA wasn't planned as a strategic moat. It was an engineering solution that became a business empire.
I've been optimizing CUDA kernels for 15 years, watching brilliant algorithms become performance disasters because nobody understood the memory hierarchy. CUDA promised to democratize parallel computing, but it actually created a new class of specialist engineers who understand thread blocks, warp scheduling, and memory coalescing. Most developers still think GPU programming is magic.
I've guided countless organizations through CUDA adoption. The pattern is clear. Those who understand that GPU programming is fundamentally different from CPU programming succeed. Those who think it's just faster CPUs with more cores usually fail spectacularly. CUDA didn't just change how we compute, it changed how we think about parallel algorithms and hardware architecture.
Dr. Martinez guide us through this parallel programming nightmare. Maria and Jamie prepare to explain why just add more cores became the most misunderstood concept in computing. No mercy, no hand-waving about embarrassingly parallel problems.
Let's start with the fundamentals. What exactly is CUDA, and how did graphics cards become supercomputers?
CUDA stands for Compute Unified Device Architecture. In 2006, NVIDIA realized that graphics cards, which were designed to render pixels in parallel, could be reprogrammed to do general-purpose computing. Instead of calculating colors for millions of pixels, you could calculate anything for millions of data points. We took hardware designed for gaming and turned it into a massively parallel processor.
The key insight was that GPUs already had thousands of simple cores designed to work simultaneously. A modern CPU has maybe 64 cores that are incredibly sophisticated out-of-order execution, branch prediction, massive caches. A GPU has thousands of much simpler cores that do basic arithmetic really fast. It's the difference between 64 brilliant engineers and 10,000 efficient assembly line workers.
How is GPU architecture fundamentally different from CPU architecture?
CPUs are designed for latency, getting one task done as fast as possible. They have huge caches, sophisticated branch predictors, and out-of-order execution to hide memory latency. GPUs are designed for throughput, getting many tasks done simultaneously. They have thousands of simple cores with minimal caches, and they hide latency by switching between threads instead of predicting branches.
The memory hierarchy is completely different too. CPUs have deep cache hierarchies measured in megabytes. GPUs have tiny caches but massive memory bandwidth up to 2 terabytes per second. CPU optimization is about cache locality. GPU optimization is about memory coalescing and bandwidth utilization. It's like learning a completely different programming paradigm.
Walk me through the CUDA programming model. How does it actually work?
CUDA organizes computation into a hierarchy. Grids contain blocks, blocks contain threads. A kernel launch creates thousands or millions of threads organized into thread blocks. Each thread executes the same code, but with different data, single instruction, multiple data parallelism. The hardware scheduler groups threads into warps of 32 and executes them in lockstep.
But here's where it gets complex. Threads in a warp must execute the same instructions simultaneously. If threads diverge, some take one branch, others take another, the hardware serializes execution. Your parallel code becomes sequential again. Thread divergence is the silent killer of GPU performance.
What are the most common CUDA programming disasters you see?
Memory coalescing failures. CUDA achieves peak bandwidth when adjacent threads access adjacent memory locations. If your memory access pattern is random or strided, you get terrible performance. I've seen kernels run 50x slower than optimal because of poor memory access patterns. The hardware is incredibly sensitive to how you organize your data.
Shared memory bank conflicts. Each thread block has fast shared memory, but it's organized into banks. If multiple threads access the same bank simultaneously, they serialize. Getting shared memory access patterns right requires understanding the underlying banking architecture. It's like trying to optimize assembly code.
How did NVIDIA build such a dominant position in parallel computing?
We got there first with a complete ecosystem. CUDA wasn't just a programming language, it was compilers, libraries, debuggers, profilers, and documentation. We made GPU programming accessible to researchers who didn't want to write graphics shaders. By the time competitors appeared, we had thousands of developers and millions of lines of CUDA code in production.
The library ecosystem became the moat. cuBLAS, cuFFT, cuDNN, these highly optimized libraries solved real problems that would take years to implement from scratch. Once your codebase depends on CUDA libraries, porting to AMD or Intel GPUs becomes a massive rewrite, not just a recompile.
What about the alternatives? Why didn't OpenCL or other standards succeed?
OpenCL tried to be vendor neutral, which meant it was the lowest common denominator. CUDA could expose NVIDIA-specific features and optimizations. OpenCL kernels had to work on CPUs, GPUs, and FPGAs, so they couldn't take advantage of any platform's unique strengths. Portability killed performance.
Plus, NVIDIA kept innovating. Tensor cores for AI workloads, unified memory for easier programming, cooperative groups for advanced synchronization. By the time OpenCL standardized a feature, CUDA was already 2 generations ahead. Standards committees move slowly, competitive products move fast.
How did the AI boom change CUDA's importance?
AI made CUDA essential rather than optional. Deep learning requires massive matrix operations that are perfectly suited to GPU architecture. PyTorch and TensorFlow both use CUDA under the hood. Every AI researcher, every machine learning engineer, every data scientist now depends on CUDA. We went from serving HPC niche markets to powering the entire AI revolution.
What are the technical challenges of CUDA kernel optimization?
Occupancy optimization is brutal. You need enough threads to hide memory latency, but each thread uses registers and shared memory. High occupancy might mean low per-thread resources. Low occupancy might mean idle cores. Finding the sweet spot requires deep understanding of your algorithm's memory and compute characteristics.
And it's hardware dependent. Optimal configuration for one GPU generation breaks on the next. Register count, shared memory size, warp schedulers, everything changes. Code that screams on a GTX 1080 might crawl on an A100. You're constantly chasing moving hardware targets.
How do you debug CUDA code when traditional debugging tools fail?
CUDA debugging is a nightmare. Race conditions that only appear under specific thread interleavings. Memory errors that corrupt data thousands of threads away from the bug. Print debugging becomes your best friend because interactive debuggers often change the timing enough to hide the bug you're chasing.
Memory debugging tools like CUDA memcheck help, but they slow execution so much that timing-dependent bugs disappear. You end up writing lots of validation kernels and checksums to catch corruption. It's more like embedded systems debugging than application development.
What about the business implications of CUDA dominance?
CUDA created unprecedented vendor lock-in. Entire industries, AI, cryptocurrency, scientific computing depend on NVIDIA hardware. Companies spend millions on CUDA development and can't easily switch to competitors. It's the most successful platform lock-in since Microsoft Windows.
And NVIDIA leverages this ruthlessly. Premium pricing, artificial segmentation between gaming and data center cards, licensing restrictions. They know customers can't switch, so they extract maximum value. CUDA's technical excellence enabled business dominance.
How has CUDA evolved to maintain its competitive advantage?
Constant innovation in both hardware and software. Tensor cores for AI, ray tracing cores for graphics, unified memory for easier programming. Each generation adds features that competitors struggle to match. NVIDIA doesn't just make faster GPUs, they make GPUs with unique capabilities that require CUDA to access.
What are the fundamental limitations of the CUDA programming model?
Not all problems parallelize well. Algorithms with irregular memory access, dynamic branching, or complex dependencies perform poorly on GPUs. Sequential algorithms can't be magically parallelized. The GPU-CPU communication overhead means some problems are faster on CPU despite GPU's theoretical advantages.
How do you decide whether a problem is suitable for GPU acceleration?
Look for data parallelism, regular memory access patterns, and high arithmetic intensity. If you can apply the same operation to millions of data elements independently, GPUs excel. If your algorithm is inherently sequential or has irregular branching, stick with CPUs. The data transfer cost between CPU and GPU can kill performance for small datasets.
What about the future? Are we stuck with CUDA forever?
Intel and AMD are trying with OneAPI and ROCm, but they're fighting an ecosystem, not just hardware. Google's TPUs bypass CUDA for AI workloads, but they're specialized in cloud only. Apple's Metal and ARM's GPU initiatives focus on mobile and graphics, not HPC. Breaking CUDA's dominance requires not just better hardware, but better software ecosystems.
So CUDA isn't just a programming language. It's a complete reimagining of how computation works, built on hardware originally designed for video games that accidentally became the foundation of the AI revolution and created the most successful vendor lock-in in computing history. This is more like industrial engineering than software development.
Welcome to parallel computing reality. Anyone can write a for loop, but designing algorithms that efficiently utilize thousands of cores, manage complex memory hierarchies, and achieve consistent performance across different hardware generations. That requires understanding computer architecture at a level most software engineers never encounter.
This episode was brought to you by Engineer Panic, where we expose how gaming hardware accidentally conquered scientific computing. Because understanding why your GPU acceleration is slower than your CPU might be more important than your theoretical speed-up calculations. We're back. Let's talk about the practical nightmare of actually succeeding with CUDA development. Maria, what's the most counterintuitive advice for engineers getting started with GPU programming?
Forget everything you know about CPU optimization. Cache-friendly algorithms often become memory unfriendly on GPUs. Loop unrolling that helps CPUs can hurt GPU occupancy. Branch optimization that improves CPU performance creates warp divergence disasters. You're learning a completely different programming paradigm.
Profile early and profile often. CUDA performance is incredibly non-intuitive. Code that looks efficient can be bandwidth limited. Simple kernels can outperform complex optimizations. Use NVProf and NSite religiously. Your intuition about what's fast is probably wrong.
Start with libraries before writing custom kernels. cuBLAS, cuFFT, and Thrust are written by experts who understand the hardware better than you do. Custom kernels should be your last resort, not your first instinct. Most performance problems are solved by better algorithms, not faster implementations.
What are the biggest red flags in CUDA development projects?
Assuming linear speedup with core count, we have 5,000 cores, so we'll get 5,000x speedup. Memory bandwidth, not compute power, is usually the bottleneck. Also, ignoring the Amdahl's law, if 10% of your algorithm is sequential, your maximum speedup is 10x regardless of how many cores you have.
Not considering the entire system. GPU-CPU communication, memory allocation overhead, and kernel launch latency can dominate small workloads. I've seen projects where the data transfer takes longer than the actual computation. Always measure end-to-end performance, not just kernel execution time.
Treating CUDA as a silver bullet, GPU acceleration only helps certain types of problems. If your algorithm doesn't have massive data parallelism, CUDA won't help. Sometimes the best GPU optimization is realizing you don't need a GPU.
How do you handle the vendor lock-in reality of CUDA?
Design your architecture with abstraction layers. Keep CUDA-specific code isolated behind interfaces that could be implemented with other technologies. But be realistic, if you're doing serious GPU computing, you're probably using CUDA. The alternatives just aren't mature enough for production workloads.
What keeps you up at night about the current state of parallel computing?
The complexity barrier. CUDA programming requires deep hardware knowledge that most software engineers don't have. We're creating a two-tier system where high-performance computing becomes accessible only to specialists. The democratization promise hasn't been fulfilled.
The vendor concentration risk. NVIDIA's dominance is great for performance and ecosystem coherence, but dangerous for competition and innovation. If NVIDIA stumbles or makes bad strategic decisions, entire industries suffer. We need more viable alternatives.
The sustainability of current approaches. Moore's law is ending, but parallel programming complexity keeps increasing. We need higher-level abstractions and better tools, or parallel computing will remain accessible only to hardware experts. The future of computing depends on making parallelism easier, not just faster.
How do you future-proof parallel computing skills as hardware continues evolving?
Focus on fundamentals, memory hierarchies, parallelism patterns, and performance analysis. CUDA syntax changes, but the underlying principles of parallel algorithm design remain constant. Understanding why things are fast or slow matters more than memorizing API calls.
Final advice for engineers considering GPU computing.
Understand your problem before choosing your solution. GPU computing isn't magic, it's a specialized tool for specific types of problems. Learn the fundamentals of parallel algorithms and computer architecture. And be prepared for a steep learning curve that's more like hardware engineering than traditional software development.
Start simple and measure everything. Build intuition through experimentation, not assumptions. CUDA performance is counterintuitive and hardware dependent. What works on one GPU generation might fail on the next. Always validate your optimizations with real benchmarks.
Question whether you actually need GPU acceleration. Many problems are better solved with better algorithms on CPUs than with parallel implementations on GPUs. The best optimization is often avoiding unnecessary work, regardless of how many cores you have available.
This has been Engineer Panic. We've learned that CUDA transformed gaming hardware into scientific computing infrastructure, that parallel programming requires rethinking everything about software development, and that NVIDIA accidentally created the most successful platform lock-in in computing history. Sweet dreams, and may your memory accesses always be coalesced.
Thanks for the deep dive. Now, if you'll excuse me, I need to figure out why our latest kernel optimization improved performance on V100s but made A100s slower, and whether that's a hardware quirk or a fundamental algorithmic problem.
And I need to explain to my team why our simple matrix multiplication kernel has 47 different optimization parameters, and why changing the thread block size by one completely destroys performance.
Keep building, keep measuring, and keep questioning whether parallelization is actually solving your real problem. The future belongs to engineers who understand that more cores don't automatically mean better performance.
This has been Engineer Panic, where gaming graphics cards meet scientific computing reality. Until next time, remember, your parallel algorithm isn't slow because it needs more cores. It's slow because parallel programming is fundamentally different from everything you learned about software development.